This video is a solution to free response question number 2 from the 2011 AP Physics C Mechanics exam. An amusement park ride features a passenger compartment of mass m that is released from rest at point A, as shown in the figure above, and moves along a track to point E. The compartment is in free fall between points A and B, which are a distance 3r/4 apart, then moves along the circular arc of radius r between points B and D. Assume the track is frictionless from point A to point D, and the dimensions of the passenger compartment are negligible compared to R. For part A, on the dot below that represents the passenger compartment, draw and label the forces, not components, that act on the passenger compartment when it is at point C, which is at an angle theta from point B. In the description of the problem, they say to assume that the track is frictionless between points A and D, and so since C is between those 2 points, there will be no friction that acts on the compartment at point C. There are only 2 forces that act on the compartment at point C. One of those forces points straight down. It is the gravitational force, and the other force is the normal force, which points perpendicular to the surface. And those are the only 2 forces that act on the compartment at that point, and so I feel that is all we need to have drawn on our diagram for part A. For part B, it says in terms of theta and the magnitudes of the forces drawn in the diagram, we need to determine an expression for the magnitude of the centripetal force acting in the compartment at point C. I'm going to draw a couple extra little diagrams up at the top that help with part B. So there are 2 points in the diagram. One is point C, and then the other point, which I've labeled in green, is the center of the circle that would describe the arc of that track that the compartment is moving through. And so I'm going to draw those separately in at least 1 or 2 different diagrams. So I'm labeling those points outside of the diagram so we can see a little bit better what's happening. And so there's a dotted line which connects those 2 points, which I'm drawing now. And then if you look at the dotted line in the diagram which connects point B to the center of the circle, that is a horizontal line, and they call the angle between those 2 dotted lines that I've drawn theta. If you continue the dotted line that I've drawn past point C, then you should be able to notice that if I extend another horizontal line away from point C, that the angle that they've drawn theta is the same as the angle that I'm adding to the diagram now, theta down below. Those 2 angles are equal. And so now if we start to draw in the forces that are acting on the compartment at point C, N points along this dotted line with this in the direction of that blue arrow, and then mg points straight down like this. And so in our equation for part B, which needs to be an expression for the magnitude of the centripetal force, we recognize that N points toward the center of the circle, but so does a component of mg. And so part of mg points parallel to the surface, but more importantly to us, there is a component of mg which points away from the center of the circle in the direction opposite of N. And so in this blue triangle that we have, there is a 90-degree angle in the sort of upper left corner of that triangle. And the angle which I'm drawing now in yellow also has to be 90 degrees. Because the mg points straight down and the dotted black line that I've drawn is horizontal, and so those 2 together make a 90-degree angle, which means that the upper angle of that triangle has to be 90 minus theta degrees. And so if we have a triangle where one of the angles is 90, another angle is 90 minus theta, that means the angle in the bottom here must be equal to theta. And the reason why that's important to us is because now we can express the component that points opposite the direction of N as mg sine theta. And so on the right hand side here, I'm going to draw just a little sketch which shows N, which points towards the center of the circle, is opposed by a force mg sine theta. And just to be absolutely clear, that is because mg, which points straight down, forms a triangle with theta tucked in that corner there, and so the component which points opposite that angle, drawn with that red line, is mg sine theta. And so when I write my Newton's second law equation for part B, I need to write that the sum of the forces that act on the compartment in the direction of the circle is equal to mass times acceleration, and the two forces that I need to include are n, which I'm going to call positive, and mg sine theta, which I'll call negative. Now normally we would write that is equal to m times v squared over r, but in the problem for part B they explicitly say to determine an expression for the magnitude of the centripetal force. And so for that reason, I'm just going to, on the right hand side of this equation, I'm going to write just FC. And so I think it is sufficient there to just say that the centripetal force, the magnitude of the centripetal force, is equal to n minus mg sine theta. Part C says to derive an expression for the speed Vd of the passenger compartment as it reaches point D in terms of mr and fundamental constants as appropriate. This is done by using conservation of energy, and we need to equate the energy at point A to the energy at point D for our initial and final instances. And there's no friction on the track between points A and D, and so the only forms of energy that we need to consider are the gravitational potential energy at A, and at point D, the kinetic energy. And so I'm going to continue working on part C down below. The expression for the gravitational potential energy will be mgh, but for h we need to be careful about the height of the compartment at point A. It says that between points A and B is a distance of 3/4 r, and then the remaining height between the level flat portion of the track and point B is equal to the radius of the circle, which is equal to r. So plus an additional value of r. If you look back at the diagram, you will see that. And that gravitational potential energy is equal to the kinetic energy at point D, which is just 1/2 m Vd squared. The left-hand side of the equation will reduce down to, if we add the 3/4 r plus r together, we'll get 7/4 r. So the left-hand side is 7/4 times mgr, and the right-hand side is still 1/2 mvd squared. If we multiply both sides by 2, we will find that 7/2, and then divide by m on both sides because the ends will cancel, so 7/2 gr is equal to vd squared, which means finally if we solve for vd, the velocity at point D is the square root of 7/2 gr. And I think that is a correct answer for part C. And now I want to move on to part D. And so part D says, if the compartment is brought to rest by friction, calculate the numerical value for the coefficient of friction mu between the compartment and the track. For this part, I'm going to start by writing Newton's second law. I know that between points D and E, the only force that's acting on the compartment is going to be the friction, and that is equal to the mass times the acceleration of that compartment. That friction is equal to the coefficient between the track and the compartment times the normal force. And I know that the normal force, because the track is level, is equal to the weight of the compartment. So mu times m times g on the left-hand side. And I know the masses are going to cancel here, but I do need to come up with an expression for the acceleration, which I think can be achieved by writing a kinematic equation. V squared equals V naught squared plus 2a delta x. We know that at point E, the compartment will be brought to rest, and so the final velocity will be 0. We know the acceleration will be negative, and so we can say that 2a delta x is equal to v naught squared, or the acceleration is equal to v naught squared divided by 2 times delta x. And so substituting that expression in for the acceleration, we should be able to find that the masses will cancel, and if we divide by g, we have an expression that's about halfway to where we want it. V naught squared divided by 2g delta x. They tell us in the problem that delta x, the distance that it travels between points D and E, is can also be expressed as 3r. So I'm going to write this as v naught squared over 2g times 3r. Lastly, our expression that we have for Vd, which we derived in part C up above, is the initial velocity between points D and E. So if the cart starts at point D and is traveling to point E, then velocity at point D is the initial velocity. And so the equation that I have now for the coefficient of friction, I'm going to substitute my expression for Vd. So 7/2 gr square root. We'll eventually square that. And in the basement of this fraction, I have 6gr. And so now this is going to reduce greatly. On the top, I'm going to have 7. And on the bottom, I'm going to have 12. And the gr in each case will cancel because I'm squaring a square root. And so the coefficient of friction between the compartment and the track is 7 divided by 12, which is about 0.6. And I think that that is quite exciting that from the information given, which is not very much, we can figure out the coefficient of friction for this compartment while it's being brought to rest by friction. Part E says, now consider the case in which there's no friction between the compartment and the track between points D and E, but instead the compartment is brought to rest by a braking force minus k times v, where k is a constant and v is the velocity of the compartment. For part 1, we are asked to write but not solve a differential equation for the velocity as a function of time. For part 1, I think all we need to do is write Newton's second law, and for the force we need to write the braking force that they've described in the problem, minus k times v. The mass of the object is m, and the acceleration can be expressed as dv dt. And so this is a differential equation that could be solved for the velocity as a function of t. For part B, it says to solve that differential equation that we just wrote. And so in order to do that, we need to use separation of variables. And so I'm going to put all my constants and the dt on the left-hand side, and I'm going to put the v on the right-hand side with the dv. And when we do that, we should get minus k over m times dt is equal to dv divided by v. From there, we can integrate both sides. On the left-hand side, the minus k and the m are all constants, and so they do not affect the integration. And on the left-hand side, we're going to integrate from t equals 0 up to a time t equals t. And on the right-hand side, we're going to integrate from the initial velocity, which is vd, up to some arbitrary velocity v. On the left-hand side, I know that the integral of dt is just going to give us t, so minus k over m times t, evaluated at 0 and t, is equal to the integral of 1 over v dv. The integral of 1 over v is the natural log of v, evaluated at vd and v. And so when I evaluate both sides of this equation at the two endpoints, I'm going to get on the left-hand side minus kt over m minus 0, and so I won't write that term, is equal to the natural log of v minus the natural log of vd. And so the natural log of a minus b is the natural log of a over b. And so I'm going to write the natural log of v over vd. And now in order to solve this for v, I'm going to exponentiate both sides of the equation. And on the left-hand side, there's really no simplification that happens. It's just e to the minus kt over m. And on the right-hand side, the natural log function will go away, and all we're left with is v over vd. And so finally, we just have to solve this for v. V is equal to vd, the initial velocity, times e to the minus kt over m. And so this equation is our velocity as a function of time. We can plug in any time and figure out what the velocity will be between points d and e, because vd, k, and m are all constants. And finally, on to part E3. It says on the axes below, sketch a graph of the magnitude of the acceleration of the compartment as a function of time. On the axes, explicitly label any intercepts, asymptotes, maxima, or minima with numerical values, algebraic expressions as appropriate. And so since we need an expression for the magnitude of the acceleration, we need to take the derivative of the function that we just found in part E2. And so the acceleration is the time derivative of the velocity. And so since vd, k, and m are all constants, the only t that's in this expression is in the exponent. The derivative will be the derivative of the exponent times the function itself. So minus k over m without the t times vd times e to the minus kt over m. And that is our expression for the acceleration. And so at t equals 0, which is the first point that I need to make in the graph, at t equals 0, we know that we would get e to the 0, which is equal to 1. And so at t equals 0, the acceleration is just equal to minus k vd over m. And so since we're graphing the magnitude of the acceleration, then I can make a point on my graph, and that point should be equal to k vd over m. And from there, I know that the function has the form of an exponential decay, and so from there, the magnitude of the acceleration should decay as such, and it should never become 0. And so I should indicate here, because of the form of the equation, that this is going to be an asymptote.